Did I? Now the recording has started, no? Yeah. Okay, so now I'll start with unit 2. Oh, no, 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 no. Wait, wait, sorry. So I'll start with unit 2. Okay, so we are going to deal with fiber optics now. So I'll just be covering what are the important parts. The rest I'll be skipping. So yeah, so introduction to fiber optics. The invention of telephone brought a major change in much of the electrical signals that transmitted in analog form to a continuously varying electric current. Okay, all of this, I think. Mm, okay, these are just basic examples for fiber optics. I think this part is something that we can skip. All of this is not required. I'm talking from exams perspective, so this part is not something that's required. So introduction. Okay, so what essentially is fiber optics? So we'll just start from that. Okay, so it's essentially a technology that is used for transmitting of something like some form of information, either in like uh through some fibers which is made up of glass and plastic and all of those. Okay, so that is your fiber optics or optical fibers. Okay, so instead of using like electrical signals, so like your copper wire and all, what it uses electrical signals for transmission. No, so but on the other hand, your fiber optics uses light pulses to transmit data. Okay, so that's up with that. So there's light source, there's transmission medium, and then the optical detector. Okay, so your LED optical fiber and your photodiode. Okay, so yeah, I think we're done with the first lecture. So second lecture, why do we need optical communication? We need to communicate, no? So the most reliable and economical and the fastest way of communication between 2 points is through EM waves. So your electronic wave, electromagnetic waves, that's your most reliable and economic and the fastest way of communication between 2 points. Okay. So your source, your communication channel, and your receiver. So you need to communicate with the help of your communication channel. So some examples for it is your radio broadcast, telephone, mobile phone, optical communication, etc., and so on. Okay. So your communication channel introduces loss and distortion to the signal. Okay. So there's some amount of loss and distortion to the signal. So, so what should a reliable communication system be like? Okay. So there should be minimal distortion. So that is the first point. Here it should have minimal distortion. And then noise added by the channel should be very little. So there's not noise should be very little. Essentially, both are the same points. Okay, there should be minimal distortion and the noise should be very little. Okay, so electric signals produced by various sources such as telephone, computer, or video are not always directly suitable for communication through the channel. Okay, so how to actually communicate? So we saw that EM waves are the most suitable ones through which communication happens. So these signals are used to modulate a high frequency EM waves, such as your radio waves, microwaves, and your light waves. So how we communicate with the help of all of these waves, so radio, micro, and light waves. Okay. So all of this. This is second chapter only, no? Okay, why is so many? I'm just skipping all of the unwanted stuff. Okay, so this is a very nice thing. So, how would you actually detect something? Okay, so you have like all of your signals are all continuous, no? So, how will you actually detect something and how do you make it discrete? Okay, so you do something called a sampling. So you divide all of this into smaller chunks. So if you don't divide it into smaller chunks, then you don't end up getting an accurate image. Okay, so and you try to make it as minute as possible. This is like a pretty large sampling. This itself is a pretty large sampling, so you don't get like a accurate thing. So, but if you again you divide it into much smaller sections, then you try to get like a much more accurate sampling. Okay, the more smaller it is, the more accurate is your model, your sampling process. Okay. So that's all with respect to this. Uh, all of okay. I think we are done with this lecture two also. There's a lot much things that is not really required. So I'm just covering all of the important parts. So what are your advantages of optical communication? So no radio frequency or electromagnetic interference. Tapping of signal is not really easy. Okay. So it requires specific equipments and it cannot be tapped very easily. So it has a longer life and then no risk in fire and sparks, and then it can withstand extreme temperature and also extreme uh, landscapes. Okay, so much compact and lighter in weight. So this is your advantages of optical communication. You really should know. So this is something that you should know. Tapping of signal is not easy. Long life, no risk of fires and sparks, can withstand higher extreme temperature and all of your extreme geographical landscapes, and much compact and lighter in weight. So what? Uh, okay, there's much of formulas over here. So that is all that you need to know mainly in this chapter. So that includes your relative index difference. Okay, that's n1 square minus n2 square by 2 n1 square. Okay, so essentially your core, no? So you have your core and your cladding. The cladding is what which protects your protective layer for your core. Okay. So this core has a refractive index of N1 and your cladding has a refractive index of N2. Okay. So this relative index difference is your N1 square minus N2 square by 2 N1 square. Okay. So for a weakly guiding fiber, that means your N1 is almost similar to N2. So at that time, your formula becomes this. Okay, that's all. These are just like the details as to what the measurement for all of your cladding, everything should be. So the innermost is the cylindrical region, which is light guiding region, this innermost region. And then it is surrounded by a coaxial middle region known as the cladding. Then you have your cladding. Then there is a coating for your cladding. And then outmost region is called as the sheath or the protective buffer coating. And then there is your plastic coating. Okay. Um, then you have your final plastic coating, and that's all. Okay, so all of these are sizes I mentioned. That's all. And then the data through the optical fiber is sent through a train of optical pulses. Okay, studying light guidance through optical fiber and its transmission characteristics enable us to understand. So the whatever the data is sent through the optical fiber, and hence we are receiving our output. Okay. So how can we optimize this transfer of data? Like what can we exactly do to optimize this transfer of data? What can be done? So that is something that we'll look into soon. So how light guided through optical fiber. So John Tyndall demonstrated that light can be guided as a curve of a stream of water. So if you see a stream of water and if you have a light source, then the light actually comes as a curve. Like, I mean, instead of traveling a straight path, it curves. Okay. So that is what he found. Okay, so I think total internal reflection and all is something that we know. So total internal reflection, it happens only when your refractive index of N1 is greater than N2. Okay, I mean N1 greater than N2. So N1 is your refractive index of core and N2 is the refractive index of cladding. So you shouldn't mix up this. So whenever is your phi greater than phi c, your critical angle, that time the total internal reflection takes place. Sorry, reflection takes place. So your phi c is your sine inverse of n2 sine inverse of n2 by n1. Okay. So total, always just remember this condition that total internal reflection happens only when the n1 is greater than n2. Okay, that is one condition to be remembered. So condition for total internal reflection, as I said before, n1 greater than n2. Okay. So then your sine phi is equal to phi c equal to n2 by n1. This you should know. And then n1 n0 sine I equal to n1 sine theta. So n1 and the sine I is your incident angle. Is sorry n0 and your incident angle. So the outside part is equal to n1 into this incident angle theta. So that is essentially the formula. If you can understand the diagram, you can just know the formula. And then all of this is just various versions of it. So if you see, this is something that will be used quite often. So sine I max, this is something that you should know. Mainly when your outside medium is air. So this medium when it is air, that means your n naught is equal to 1. Okay, so by substituting in your initial formula, you will essentially get sine I max is equal to root of n1 square minus n2 square. Okay, this is a formula that will be very frequently used. Okay, so yeah, it's the same thing that we have discussed. Okay, now numerical aperture. Okay, so what is numerical aperture? So it's someone showing. Okay, it's Nagadeep. Okay, so numerical aperture. We've seen that the rays launched into fibers are limited to a maximum acceptance angle for guidance through the fiber. So if you see the incident ray that gets in, there is a maximum acceptance angle, incidence angle, acceptance angle for this fiber. Okay, so that is called as a numerical aperture, and we've already discussed sine I max is equal to n1 square root of n1 square minus n2 square by n naught. Again, reminding, don't mess up with N1 and N2. N1 is your refractive index for your core and N2 is the refractive index for your cladding. Okay, for air, your N0 becomes 1 and that's why you got this. That is something that we looked into right now only. Correct? So your numerical aperture is essentially this. So it's sine I. Okay, so sine I max, that is your N1 square, root of N1 square minus N2 square. So that is your numerical aperture as well. So if you see, if you compare it with the previous formula, this the del where we got a relative index difference. So there also, if you substitute and see, you will essentially get numerical aperture is equal to n1 into root of 2 delta. Okay, so it's just the same thing repeated over again and again. One. I think they've just shown the derivation and how it exactly happens. So you have to remember all of this. So sine and this thing. These are the ones that will be repeatedly used. Okay, and then even this formula, it depends on what the data is given. So depending on that, it changes. Okay, so your example is given, your N1 is given, N2 is given. What should you find? Okay, I max and all of that you have to find. So first you can find your delta, it's n1 square minus n2 square by 2 n1 square. Okay, so you will get 69%. And in your numerical aperture, if you know n1 and n2, you can find a numerical aperture also. You found it to be 0.17. And then when your maximum acceptance angle when N naught is 0. So she N naught is 1 because for its R, no, I told you before. So it will be sine inverse of NA by N naught, but N naught is 1 over here. So sine inverse of NA, sine inverse of 0.17, 9.8. Then your maximum angle in water. Okay. So in water, your N naught is 1.33. And then I think even in glass, I forgot, but I think it is 1.81. I'm not sure, but just know the refractive index for glass also. So same thing, if you substitute, you will get 5 max. And then more other numericals on the same. Maybe you can, okay, in optical fiber, the core material. So core again, core I told it's N1, correct? No? And then has a refractive clad index of the clad materials is 1.4, that is N2, your propagation angle. So your cos theta is equal to N2 by N1. You will get your answer. Your theta will be cos inverse of whatever this is. So you'll get your answer. Yeah, I think you can just leave it with this step also. That works. Okay, a core has a media. Okay, N1 is given. N2 is given. What is your critical angle? So it's N2 by N1, right? No, sine phi is equal to N2 by N1. That is your critical angle. You will get your answer. Then also calculate the angle of acceptance. So angle of acceptance, I previously showed this formula. If not, please note it down. So sine inverse of root of N1 square minus N2 square. Again, do all of your substitution, you get your answer. This fiber optics and acoustics, ultrasonics, everything is just direct formula application. I don't think there's much of numericals that could be asked. Only maybe in your A mode, B mode scan is something conceptual. Otherwise, it's all direct formula application. As long as you know what all of the formula represents. Okay, you just need to know the representation of the formulas. So again, N1, N2 is given. Your NA is root of N1 square minus N2 square. Get your answer. Your acceptance angle is sine inverse of root of N1 square minus N2 square. You get your answer. Same thing. Again, and you're finding NA here. You're finding sine theta here. The acceptance angle. It's just manipulation of all of these formulas. Just the 4 5 formulas that you have. Just manipulate all of that, and you will end up getting any and every answer. And then again, this is something that we didn't deal with as much. So here they've given you the refractive index change. They've given numerical aperture. So if you need to find the refractive index of your core, then you use this formula and you find it. And if you need to find the refractive index of your cladding, then you again substitute back in this formula, which initially gave you the refractive index change, your delta. So N1 minus N2 by N1. So you get your N2 there because you know your N1 from here, this formula. Okay, that's all. So that's what, as I said, it's just manipulation of formulas. So again, these same 2 formulas. Here they're just finding delta N1 minus N2 by N1. Just don't ensure that you don't mess up the N1 and N2. Otherwise, you're all well and good. You can use the same formulas and you can do. Otherwise, it just gets interchanged. That's all. Okay, so N1 is this, N2 is this. Again, the same thing. So we can skip this part for now. Okay, so what is the necessity of cladding? I think it's better to know this. So keeps the size of the fiber constant and reduces the loss of light. Okay, so mainly it reduces the loss of light. So, I mean, we are you doing all of this for efficient transmission? No. If there is loss of something, then why would you need this? So, this is like a protective layer. So, to protect it from any physical damage, and then prevents leakage of light energy, and then from the fiber, and then it prevents leakage of light energy from the core through any frustrated TIR. Okay, and it reduces the cone of acceptance and increases the rate of transmission. So the acceptance cone is reduced and then the transmission is more. Okay. So a solid cladding instead of air makes it easier to add other protective layers over the fiber. Okay, so more protective layers can be added. As we saw after the cladding, the plastic layer was added and all of that was there. No, so it's better to know all of this in detail. I don't think this is required as much, this formula. But otherwise, let's just know what ray path in graded indexes. So initially we saw what the step index is. So what did we see before was that when there's when there's an incident ray, then it gets reflected, reflected, and then there is one final uh, final output that we receive. Okay, so if you try to increase uh, if you try to change the incident ray such that there is more amount of reflections, and hence you receive like a higher numerical aperture over here. Okay, so similarly over here. So how can we make it more efficient is that question, no? So in a uniform medium, it just goes like this, right? So what should you do? You have to try and increase the number of reflections inside the medium, no? So for that to happen, you can actually have a graded index. So there's different, earlier we just saw N1 and N2, no? Two different refractive index. But let's just assume there are different refractive index, okay? So in that case, it bends towards the normal, like all of that. And then you end up, uh, so as the refractive index of a GI varies with the radial precision, the ray cannot travel in a straight line but follows a curved path. So it'll end up following a path like this. So limitations of ray theory. It does not tell about the discrete modes of fiber. And then when light is guided to the fiber, some light also extends to cladding. So some light also like escapes from the core and it goes to the cladding. So ray theory can't explain this, why this happens essentially. And then geometrical optics are valid only for diamonds much larger than the wavelength of light. So all of these rules that we have studied is only works when the dimensions is uh, greater than the wavelength of light. Otherwise, then everything is just redundant. No? So that's all. So we'll just move to the next part. So models of fiber. Mm, okay, one second. Okay, modes of propagation. Okay, all of this uh, we don't really have such. What happens if we change the wavelength of light coupled to a given fiber? Okay, wait, this. Hmm. Okay, this V number formula, I think this part is there. Okay, so I am not really sure about the other parts. I'll do check out and let you know because I don't think I covered all of this part for myself. Uh, Only these V number formulas is very essential because only with these two formulas you will have all of your manipulations. You manipulate all of these two formulas and you end up getting your answer. That's all. So your core radius, okay, the radius of your core is your A. Your numerical aperture, we already know Na. Otherwise, you know the formula to find Na also. And then you know the wavelength of the light is lambda naught. Okay. So all of this we know. And then N1 is your refractive index of your core. N2 is your refractive index of your cladding. So when your V number, your V is less than 2.4, then your fiber supports only one mode, that is single mode fiber. Okay. So there is just one ray that is passing inside. What a single mode na? Like one incident ray passing into your system, chlor cladding system. That's all. If it is greater, na, then there's multi mode. Okay. Then intermediate values of V. I think single mode and multi mode is more than enough. Mostly you will be asked to check whether it's a single mode fiber or not. So you use your formulas, you manipulate all of your formulas, you will be given most of these information. If not given also, you will not be given NA. Okay, so you might have to find what NA is. That is essentially root of n1 square minus n2 square. So I think you will otherwise also you will be able to get to the answer. You will be able to find V number. So if V is less than 0.4048 now, 2.4048 now, then it is a single mode fiber. That's all. That's what you need to conclude. So this question is definitely expected. Okay, so you just be thorough with that. So single mode now, used in long haul just characteristics on where and when and how it is used. So uses generally laser diode as light source, small pore with diameter this much, and then coupling joining two fibers is difficult because it has a very small core. You don't really have enough space to actually join fibers and all of that. So it becomes very tricky in that sense. So precision equipment or components are required. So yeah, and then multi-mode fibers suitable for your local area network. So you just have like study. So this is for your long haul optical communication, and this is for local area. Multi-mode is for your local area. Has a core diameter of this much, 50 micrometer, and then coupling light into it is easier. And then this is your light emitting diode is used. Here it's your laser diode, the single mode. Here it's your light emitting diode, LED. Here it's just LD. Um, and then all of your values, and then your system components or your equipments are cheaper. Okay, that's all. I think these are the types of questions which I told. So if you see here, they've given you N1, they've given you delta, they've given you A, which is the radius of your core. Now find the range of the wavelengths in which the fiber would be single mode. So for it to be single mode, the V should be less than 2.4, correct? No. So how will you find NA with what and all data? See, one your formula is here, root of N1 square minus N2 square. The other one is just take N1 into root of 2 delta. So with that, you find your NA. Then you substitute in the formula. I think all of the values are given. So you substitute in it and then you'll end up getting your answer. But here, instead of getting the V, okay, they're asking you to find the wavelengths. Okay. So your V number is then they've given that it is single mode. So it's 2.4048. So you need to find your lambda. That's all. Your wavelength you need to find and you're done with it. So for your lambda, it's micrometer over here. Don't mess up with the SI units. How many modes will this support at this wavelength? So they've given you the wavelength. So they're asking you how many modes does it support. So you find your V number and hence you conclude with your answer. Okay. And what else? I think it's the same thing. Okay. I think it's just whatever we have covered so far. Wave theory predicts discrete modes of propagation in a fiber. And then the number of modes, the V number depends on the values of the core radius, the numerical aperture, whatever is there in our formula, no? All of that it depends upon. And V is less than 2.4084048 na single mode. Greater na it's multi-mode. Then your single mode fiber has a smaller core. Okay, like we already saw, no, it's a very smaller diameter also was very smaller. But your multi-mode fiber has a large core. We saw some 50 micrometer something we saw, no? So yeah. And then both single mode and multi-mode fiber can be both your step index and your graded index. Okay. So that's all. These are the points that you can remember per se. So we'll move on to the next part. Okay, so the data transmission. So when there is data transmission, when there's some amount of data, we saw how to optimize the transmission of data. But however we try to optimize, there will be some amount of loss that we can expect. Okay, that is mainly your attenuation loss and then your broadening of the pulses. There's also dispersion also. That's what we'll deal with everything one by one. So, I mean, again, coming back to the first chapter, this 10 log loss in dB is 10 log P in by P out. Okay. So, they'll give you, so this is something that you can remember so that based on the values, you can find the loss in decibels. That's all. So, yeah. Then your loss coefficient, that is your alpha, is equal to 10 by L log 10 P in by P out dB by kilometer. So, in mainly this chapter, you just need to remember all of these formulas. If not, at least just the logic of the formula so that you know you derive the formula on your own. And then, but you won't have enough time for it, so it's better you remember all of this. If you just note down what and all they give in the question and what they ask for, you can easily identify what to use and what not to use. Okay, so it's just manipulation of formulas and rearranging, substituting, and all of that, and finally ending up with your answer. That's all. So okay, so if you see here, attenuation losses. Okay, loss mechanism. Uh, so absorptive loss mechanism. So intrinsic absorption by primary constituent materials of fiber. Extrinsic is losses due absorption by impurities. So due to the losses due to impurities is one such extrinsic loss. Intrinsic loss is based on the materials of the fiber. Okay, that's all. And then you have your Rayleigh scattering. Okay, based on small inconsistency, then there is Rayleigh scattering that happens. And then Fresnel reflection. So there's this reflection that happens at the output end. That's all. So there's Fresnel and Fresnel so Fresnel and Fresnel reflection, no, it usually happens when there's dispersion. So just remember that it's reflected black into the fiber at output end. Okay. So this is the diagram that you need to remember. So if you see here, the Rayleigh scattering at shorter wavelengths. So if you see at the shorter wavelengths around here, you see Rayleigh scattering, this blue line. And then IR absorption tail at longer wavelengths, SiO, silicon oxide vibrations. Okay. And then there's impurity absorptions at the respective wavelength. Okay. So all of your OH ions are actually absorbed at the wavelengths. Okay. So this is your OH. Here it's absorbed the highest. OH is absorbed the highest over here. You know what? They actually asked this for 10 marks. This was the one of the questions for 10 marks. So I understand that you won't be able to write enough for 10 marks, but I think you have to like draw this diagram, write these 3 points, and yeah, that's all. So yeah, and then okay, attenuation extrinsic losses. Okay, this is caused mainly due to the external factors. So what are the external factors? So if you try to like combine two wires or something due to fusion, when you're trying to combine two wires or something, and you're trying to split something, there is some amount of loss that is there. Okay, you can't really do whatever and anything and everything, no? So there's some amount of loss. So typically around 0.2 dB to 0.5 dB of extrinsic loss is there. So whatever we saw was just in intrinsic losses. So all of that Rayleigh scattering, IR absorptions, and then the impurity absorptions, all the intrinsic, some of the extrinsic ones are the mechanical splicing and your fusion, your joining and splitting of it. So at a bend, so if you're trying to bend something, the angle between the normal and the ray might be less than the critical angle. So the ray is not reflected, but it is radiated. So if the angle is less than the critical angle, then there's no TIR that is happening. There's no total internal reflection that's happening. So it gets radiated. So it goes outside. So this is the bending losses. Okay. So there's a micro bend losses. That is what we are talking about. So yeah, now when it comes to attenuation, you have to talk about intrinsic losses, extrinsic losses, to talk about all of this in detail. So yeah, I think the PYQs should help a bit with respect to how the questions could be asked. Then okay, we saw about attenuation. That is one type of loss. We saw extrinsic, intrinsic. Now we'll see dispersion. Okay, we'll see dispersion. What is dispersion now? Change in phase velocity with wavelength. Okay, so okay, once again, I'll just check how much is there. I'll try to cover in like 20, less than 20 minutes. So intermodal dispersion. So increase in pulse with the due to the variation in the propagation times of the different modes at the same wavelength through the same length of the fiber. So the length of the fiber is same. There's same wavelength also, but there's variation in the propagation time. So each mode, no, so there are different modes. So each mode starts at a different time. So when it starts at a different time, that is called as your intermodal dispersion. Okay. So the dispersion in optical fibers, there are three reasons why it happens. So there's intermodal dispersion, then there's chromatic dispersion. So increase in pulse width due to the variation in propagation of time of same mode, but different wavelengths. It's the same mode. Okay, the mode is same, but there is different wavelengths. Here it's same wavelength but different modes. Here is just the opposite. Okay, so this is due to the refractive index change in the wavelengths. So if you see one mode with different wavelengths, due to the refractive index change with wavelengths, you find chromatic dispersion. Okay. So this is just intermodal dispersion. All of this I don't think it's required. So these are just complex formulas. I'm pretty sure that these are not required. So we move on to the next one. So if you see chromatic dispersion over here, this is just a representation. Okay. Okay, so superposition of large number of plane waves of different wavelengths. So we saw here, no, same mode with different wavelengths. The superposition of it is your pulse. I think okay. Then you have your waveguide dispersion. Okay, so your waveguide dispersion is nothing but it is based on the structure of your design. Okay, the structure of your whole system. Okay, it depends on the design of the whole system. So change in the pulse width due to the variation in propagation time with wavelength, which depends on the waveguide design. So there's a fault in the waveguide design itself, in this whole system design itself. So that only decides how much of the data transmission happens to the core. No, so okay, yeah, it's given here. Decides the degree of confinement of the power within the core region. Okay, so this waveguide dispersion is generally negative. Okay, yeah. So the total dispersion is just the sum of all of this. Okay, so it's your intermodal, your chromatic, and your waveguide dispersion, and this is your relationship between them. So your intermodal is greater than the chromatic, greater than your waveguide. Usually, this is the losses that you find. So how do we reduce dispersion? So as we saw before, we have to reduce the time delay between the different modes. When there are different modes, you need to reduce and try to like make them same, no? So if you see for step index, you just have N1 and N2, and you actually uh, So based on your N1 and N2, you have your glass and the core and you just transmit, it gets reflected back and then you get your output pulse, right? So this is your step index. But can you make it much more better? So that's when you get your graded index. Okay. So here there are multiple refractive index, right? There's multiple refractive index, right? So this gets every single place, it gets bent and bent. And if you see here, the gradual changes in the refractive index. So everywhere there's a different refractive index. Here we just had N1 and N2, two different refractive index. But here it's different refractive index. So it gets bent and bent and bent. And eventually all rays are theoretically focused along the fiber. So this happens because the light rays traveling to the center sees higher index and is slowed down. So here there's higher refractive index near this area. And as it goes and goes and goes, it notices a lower refractive index and it starts bending like this. Here, if it starts from here till here, then it starts bending. Okay. So depending on where it starts from and the refractive index, it speeds up or slows down. So this is your refractive graded index when compared to your step index. Okay. So this is much more better. But this is for your multiple modes. This is for your single mode. I mean, this also works for multiple modes. Oh yeah, multiple mode fiber. Minimization of intermodal dispersion. So what did we see about intermodal dispersion? We uh, saw that the wavelengths were different and we had multiple modes. So how do we like make them better? So that's why we have something called as graded fiber index. So instead of using step index, we can try to use multiple refractive index and okay try to at least make their speeds catch up. Like this is starting early, so we will ensure that it travels a longer path. But this is starting like this, so we'll ensure that it takes a shorter path so that both of it somewhat comes nearer. Okay, so that is our ultimate goal. And again, the same formulas, V number. This is extremely important. So, so this is what the evaluation began with. Started with single mode, multi-mode fibers, then graded index, step index multi-mode fibers, graded index multi-mode fibers, and then step index single mode fibers. Okay. And this graph is something that you need to know. As we already told, waveguide is always negative. Yeah, that's all with respect to this. With this chapter, I think you need to mainly practice all the questions from previous question papers. You can practice all the questions. Um, so 1 second, I'll. Okay, so classification of fibers. So based on material, based on modes, and okay, so based on the materials, it is glass, plastic. So modes we saw single mode and multi mode now, and based on index profile, step index and graded index. So this is just a general flow chart that you can remember. And this is again something that we already saw. So single mode step index, multi mode step index, multi mode graded index. So this is the entirety of in just one slide. And again, these formulas that we already look into, intermodal, intramodal, and then the waveguide. So intramodal essentially is the chromatic dispersion. Don't get confused. So we've already talked about the V number. So it has to be less than equal to 2.4 for it to be a single mode. Otherwise, it's multi-mode. And then you need to know the applications. I mean, it's used in field endoscopy, small weight like loss, no? So we need to have lesser loss. So high bandwidth, EMI free transmission, secure transmission, and capability to withstand higher temperature and like uh, very fierce geographical landscapes. And yeah, so with respect to this, so your analog to digital converter. So when you have your analog signal, okay, when you have your analog signal, you have something called as your drive circuit. Okay, this is a very important topic. They'll definitely ask you in your 3 mark or your 5 mark. I feel like it. So, and you can just draw this and give like a brief explanation, which you do. So you have your drive circuit, and then your source. So it could be your LED or your LED laser diode or your light emitting diode. So this connector and optical splice is just to ensure that the losses aren't as much. Okay, so at regular intervals there is splices in the connectors so that for longer distances it remains proper. So your receiver and your transmitter, you have all of those. That's what end of the day, your digital thing, you're actually converting to your analog with the help of your detector, amplifier, and your restorer. Okay. So this is your receiver part. So with the help of it, you're converting into digital to analog form. That's all. So this is something, this is like, this you can know this as points. You could be asked. So, okay, compactness, high modulation bandwidth, high output power, low dispersion. All of these are just general points. Okay, so for it to be a proper light source, it should have compactness, high output power, it should have low dispersion, no losses as such, and then low threshold current for longer lifetime, and then so low loss and low dispersion, low chirp, high wavelength stability, and tunability. So yeah, that's up with this. And then you have your LEDs and laser diodes. That's are your two basic light sources, no? So, okay, these are your, so this is your surface emitting and this is edge emitting. So it's emitting from the edge, so edge emitting LEDs, so surface emitting LEDs. That's all. So you just, okay, these are just, you just need to know the difference between your LEDs and just know what, just know these definitions alone. Pin diode, na, it improves quantum efficiency at longer wavelengths. And APD, avalanche photodiode, more charge carriers for each incident photo through avalanche effect. Okay. The all of these are just very theoretical. This part is not really required. So special kinds of fibers, all of those are not required. So just the three detectors can be of T types, and what are these T types? That is something that you need to know. And what are LEDs and laser diodes? That is something that you need to know. It's all theoretical because it's all numbers and stuff. There's nothing much to cover as such. So now we'll move on to the last lecture. So we'll just see what is over here. I think not. I think we've covered most of it. So I'll just look into what exactly is there. Okay, so your fiber optic sensors. Okay, so you have your extrinsic sensors and your passive sensors. So like your temperature, so it senses your displacement or your pressure. So any physical stimulus like your temperature, pressure sensor, sensor, humidity sensor, and all of that. So that comes under your extrinsic sensors, and your intrinsic sensors. Okay, it's like a tongue twister. So your interferometric sensors, it senses pressure, temperature, and strain. Gyros, angular rotations, and your current sensors, senses high voltages because current sensor, no? What else can it do? Okay, then your displacement sensor. So essentially your input fiber, no, it is connected to your transmitter, and then output fiber is connected to your receiver end. Okay, so this displacement of one fiber with respect to the other, it is, see, if there are two sensors there, how much is it displacing from one another? This what is what the displacement sensor will sense. Okay, so the lateral displacement and the longitudinal displacement will sense and will give the output. So passive sensor are both are on a fixed platform, and detected intensity is a function of the distance of object from the fiber. Again, the same thing. How far has it displayed from one sensor to the other? Okay, so if source is here, if this is some crack or something that we notice, how far is the source, is this crack from the source? Okay, that will be detected by this. Okay, so yeah, otherwise all of this is done. So you have your pressure sensor also. So depending that will sense the pressure. I think it's only you have to know what is the difference between extrinsic and intrinsic sensors. What is the displacement sensor in detail? Like you can just write one or two points. Otherwise, and then temperature sensor. So this is also very important. So I think okay. So your temperature sensor. So using two bimetallic strips. Okay. So as temperature increases, the bimetallic strip bends because due to heat, a metal bends, no? So due to the difference in the thermal expansion of two metals. Okay. So when you see a source and the destination, source and a detector. So how do I explain this? So as there's transmission signal, there is like the bimetal strips over here. So it bends, okay? So and then based on the bending, it gets reflected. So based on how much it bends, there is a temperature sensor that is acting up. And here it's microbend temperature sensor. So uh, this this bimetallic strip, no, it'll get crammed by these two which applies pressure. Okay, these two strips that apply pressure for this bimetallic strip. With this, we will so essentially there are bimetallic strip, no? So when based on the source, that the this bimetallic strip will get bent, and then that will get detected, and then this bending will actually make will ensure this pressure takes place. Okay, so this gets this pressure here, so this wire bends over here. Okay, so this is what your microbend temperature sensor using bimetallic strip for applying pressure. So your my bimetallic strip bends because of heat, and then this pressure is applied, and your wire bends. And finally, your max Zedner. This is also like a very probable 10 marker. So essentially, there's nothing. Okay, so this input A, B, C, and D. Okay, so it could go through A, it could go through B. So your output either it will be same phase as I. That is, if it goes from A to C, that means there is no phase difference that is there. But from A to D, if you go, there's 90-degree phase difference. So that is what it's telling. So intensity, it will just get divided. Okay. If I'm getting starting with I as intensity in A and B, it will get by 2 in C and D. Okay. So the phase only, it depends on which path you're taking. Correct. No. So now let's start from source A. Okay. Now, if I'm going from source A to source C, that means same phase. No, A and C, same phase. Output gets divided by 2. That I already said. From A to D now, output gets divided by 2. It's 90-degree out of phase. Again, it goes here. Again, there are 4 paths that you can take from them. E to H, E to G, F to G, F to H. So let's now see from E to G. So if you E to G, if you see, this is the thing. So same phase. And then from E to G, there is same phase. Okay. And then similarly, from from F to G, you see here, there is 90-degree already phase difference over here. And then again, there's another 90-degree. So there's 180-degree phase difference. And then there is phase change due to travel. So here there is phase change due to travel from F to G. That's all. So yeah, if you add both of this, it will become 0. Then here it is it starts from E to H. So there's phase difference over here, 90-degree out of phase. Already it was I by 2 over here. Now it becomes I by 4. So even here, previously it was I by 2. It becomes I by 4 here. It just by 2. Okay. It just gets split by 2. And then from F, it is coming to H. Am I doing, yeah. Wait, from F, it is coming to H now. This part, it is 90-degree out of phase already. And then phase change due to travel. Then E to H is 90-degree with respect to I and phase change due to travel. So yeah, that is up with there are just four combinations over here. And then here, however it goes. So every time intensity goes by 2. And then phase difference, it depends on which path it is traveling. Okay, that's all. So I think I've covered everything. Otherwise, all of this is just not required as much. All of this is just additional stuff. So yeah, I hope you understood. Uh, Thank you so much.